Hello everyone, this is Sinan Ertemel. Welcome to my 9th lecture, which will be on mixed strategies. Remember when I talk about Nash equilibrium, I said that Nash equilibrium always exists. However, not necessarily in pure strategies. Then we should allow for random strategies. So I'm going to introduce the example where pure strategy Nash equilibrium does not exist. It's the game called matching pennies. 2 players, Ann and Bob. They have coin in their hands. And they will shove to each other simultaneously at the same time. Okay? If 2 people have the same side of the coin, player 2 Bob wins. Otherwise, Ann, player 1 wins. Accordingly, let's create our payoff matrix. So heads and heads, Ann is losing, -1, Bob is +1. Tails and tails, the same result. Ann losing, Bob winning. And the other 2 cases where they have opposite sides, Ann wins +1 and Bob loses -1. So first of all, we see that there is no dominated strategy. Therefore, we look for the best responses. And if you find the best responses, they do not coincide. So there is no pure strategy Nash equilibrium, because Ann would like to make the coin different than Bob, and Bob would like to make the same. So there is no way that their strategies converge in Nash equilibrium. So what are the random strategies and how do we find them? That's what I will show you in this lecture. But we all guess that in the equilibrium, Ann and Bob will be playing heads and tails 50% of the time. So if we are talking about probability, playing heads will be 1/2 and playing tails will be 1/2. So I am going to show you how we find these numbers. But before that, I would like to introduce similar games without any pure strategy Nash equilibrium. The game that we play when we were children, rock, scissors, and paper game. So rock beats scissors, and scissors beats paper, and paper beats rock. And if we translate this information into this matrix and find the best responses, we will see that there is no pure strategy Nash equilibrium, which makes this game fun to play. And I would also like to highlight this randomization. I mean, we shouldn't have any pattern in order to not lose advantage against our opponent. So if you are doing randomization, and the equilibrium strategy will be 1/3 of the time playing rock, 1/3 of the time play scissor, and 1/3 of the time play paper. But this 1/3 of the time, it has to be completely random. If you do some sort of pattern, first rock, then the second game scissor, and the third game paper, then after a couple of tries, your opponent will understand the pattern that you are using, and it will take advantage of you. So the best poker players understand this idea. So they know if they can calculate the bluffing probability, which they do in their free time by running computer simulations, the best world-class players, then that number, like suppose it is 1/3. If I have this hand, 1/3 of the time I should bluff. They should make the number 1/3 completely random. Like come up with some scheme where maybe they can find the difference between the 2 sides of the clock and divide it by 3 in order to make it completely random. So I would also like to touch on the field of game design, how game designers come up with a design which makes the gameplay competitive. And they are imitating rock, paper, scissors type of games. So if you play some simulation games, you might know that archer beats pikeman and pikeman beats horseman, and the horseman beats archer. So we have something very similar, exactly similar to rock, scissors, paper game. Accordingly, the optimal strategy will be unpredictable, completely random. Like 1/3 of the time you should play archer, 1/3 of the time you should play horseman, and 1/3 of the time you should play a pikeman. So Nash, in his celebrated paper, showed that every finite game has a Nash equilibrium. So we should introduce randomness via the idea that each player is assigning a probability distribution over pure strategies. So in the matching pennies game, what I mean by the probability distribution is player 1 N is gonna play heads with probability P and tails with probability 1 minus P. And in the equilibrium, I need to find the number P. Similarly, Bob is playing heads with probability Q and tails with probability 1 minus Q. So what is the equilibrium property? In the equilibrium, each player should stay indifferent among her pure strategies. So being indifferent means you get the same payoff. And in this context, payoff is expected payoff. Okay, you don't know what your opponent does. So, but there are probabilities. Like look at N. N doesn't know what Bob does. But there is probability Q that Bob plays heads, and probability 1 minus Q he plays tails. So the expected payoff will be the weighted average. So if N is choosing heads, with probability Q she will get -1, and with probability 1 minus Q she will get +1. Expected payoff is the weighted average, so it's gonna be -1 times Q plus 1 times 1 minus Q. And similarly, you will find the N's expected payoff when she plays tails. Okay, then it's gonna be either 1 or -1. 1 with probability Q and -1 with probability 1 minus Q. And you take the weighted average and you will find 2Q minus 1. In the equilibrium, expected payoff for N playing heads should be exactly equal to expected payoff when she plays tails. And if you equate these two numbers, you will find that Q should be 1/2. And you do the same thing for Bob. You equate expected payoff playing heads to playing tails, and you will find the probability of playing heads for N. So this is very interesting. So you find probability Q, which is Bob's probability that he plays heads, by equating N's expected payoff. So this is the main motivation of randomization. What's happening is each player, by randomizing, making his opponent indifferent among his pure strategies. And if we solve for P, you also get 1/2. Mixed Nash equilibrium are basically these probabilities. So the mixed Nash equilibrium is where N plays heads with probability 1/2, tails with probability 1/2, and similarly Bob plays heads with probability 1/2 and tails 1/2. That will be our mixed Nash equilibrium. So the basic lessons we can draw from mixed strategy Nash equilibrium is each player is choosing her probability according to the fact that that particular probability distribution is going to make her opponent indifferent. If you can do this right, the other player will get the same payoff by playing either of the strategy. So going to rock, paper, scissors, So you are playing 1/3 of the time rock, 1/3 of the time scissor, and 1/3 of the time paper, like, so that whatever the other player does, he will get the same expected payoff, which will be 0. So the other player becomes indifferent among his pure strategies. So this is all for today's lecture, and in the next lecture I will talk about sequential games. Thank you very much, and see you all in my next lecture.